I'm Prabhu. My actual name is Prabhakaran, but my pet name is Prabhu. Also, people call me as Kuti as well. So, um, once again, good evening, everyone. And I thank Bangalore Astronomical Society for holding such a session, not just one. Also, we have more sessions in the following days, particularly in this time of crisis where we cannot go out. I hope you all well and safe. So, in this session, I'm going to cover planetary astrophotography. As Pushpa introduced about myself, I've been doing this astronomy for the past, let's say, 8 to 9 years. I've been seriously doing astrophotography for the past 4 years. And just like anyone else out there, I started astronomy right from the basic equipment. The first equipment that I have, which still I have, is an Astromaster 130 millimeter reflector telescope. I think that's the most affordable telescope for everyone. I'm sure most of you must have owned it or still having it. So I started from that, and then I upgraded to other bigger aperture telescopes as well. When I was working in Space India, so I had opportunity to handle 8-inch reflector telescope, and I learned a lot with the telescope. And also over the course of time, I moved to UAE, and I was able to procure more bigger telescopes. And now I'm doing some sort of, you can say, intermediate astrophotographer, not expert nor advanced. It's an intermediate astrophotography, what I'm doing. So still, I'm yet to produce nice high resolution images, but so far I'm happy with whatever I'm getting. And this talk gonna cover some basics and also some in-depth information about planetary astrophotography. I have a presentation, and then after the presentation, I'm gonna show the softwares. We're gonna see how to process the images and with the necessary softwares required. Also, by the end of the session, if the sky is clear, Anish will take over the session to do live imaging. And if the sky is not clear, I have a telescope here, as you can see. And with this, I'll show you how to set up the telescope and how to take images with the videos that I've already taken. So we'll be able to cover all the aspects. So before we begin, I think few of you haven't muted your microphone yet. So there are few things which can happen as the session goes on. First thing is the session may end abruptly because of internet network failure. So if it happens, I'll again resume the session, and you can click the link and you can resume back as well. And the second thing is, if you have any questions, you can enter the question in the chat box, which is down below or to the right hand side. And the questions will be answered by the end of the session. And also, in between the session, I'll be changing the screens from the presentation to some folders where I can show some examples of the pictures and videos. So if the screen gets stuck, just wait for a while. Hopefully it will resume soon. I hope you all can hear me loud and clear, right? Okay. So let me just share the screen. So this is the presentation, planetary imaging and processing. So the background image that you're seeing is a crater, which is called Gassendi. I believe it's 110 kilometers in diameter, which was captured with the Celestron 11-inch Schmidt-Cassegrain telescope, HHT, with the planetary camera. So here you can see the details. The resolution is nice, and it was captured doing a good seeing. You can see the central peak mountains and some wrinkle edges, relays, and the crater wall. So this background image will be throughout the presentation. So planetary objects, what we can, the number of objects we can shoot with our telescope, or in other words, the planetary objects or planets like Mercury, Venus, all the way till Neptune, and we can also capture Pluto as well, but not with amateur telescope, with professional big aperture telescopes. And then Moon. So this is a separate planetary astrophotography called lunar imaging, high resolution lunar imaging. So we can capture moon as a full disk image with a DSLR camera attached to a telescope or to a lens. We can capture it as a full disk image, and the high resolution lunar imaging is something different. So high resolution lunar imaging is capturing the surface details of the moon, such as craters, and then Maria, and then highlands, and then wrinkleages, and various features you can image. The next is moons of other planets. So we can also image moons of other planets, such as Jupiter's moons, Ganymede, Europa, Io, Callisto, and then Saturn's moon, Titan, we can also photograph because of the size as seen from Earth. It's imageable. And the next thing is Sun. So this is something called solar astrophotography, solar photography. We can use solar filters, and you can attach it to the lens or the camera, uh, or telescope, and you can take high resolution images. Also, there are special type of telescopes like solar telescopes, which are being used to capture more profound images of the sun. And then capturing satellites like International Space Station, and then other satellites which are orbiting our Earth, which are possible to capture as well with big telescopes. So let me share the picture of the objects which I've mentioned here. So I've captured all these images in different time period, starting from 2018 till now. So you can see sun that was captured with the solar filter, white light image, and then Mercury captured with the 11-inch Schmidt-Cassegrain telescope, followed by Venus that was also captured with the same telescope, and then you can see the moon that was captured during the supermoon. I believe it was in 2018. And then the next is Mars. You can see the surface features very well, polar ice caps and some planitia as well. And the next is Jupiter. You can see one of the moon of Jupiter, which is Ganymede, on the top left. And the same moon you can see at the bottom right. That's a magnified version of Ganymede. You can see some surface details. The next is Saturn. You can see the rings, and you can see the Cassini division, but you cannot see the other divisions of the ring. There is another division which is very well resolved in my other image. You can see the Encke division. And the next is Uranus and Neptune. So Uranus and Neptune, these are pretty small as seen from Earth. These are faraway planets. These are highly challenging to photograph, but with a good telescope, with right equipment, you can get some details out of it. Let me move to the next slide. So let's break down all the necessary things to do planetary imaging. The first thing is choosing the right equipment. So I believe the few of the people must be starting astronomy just now and wondering which equipment to choose. So if you already have some telescopes, or if you have some equipment, then you can exploit it first, and then you can move on to, you can upgrade to another equipment. So I started with a small telescope. Let me just show you. Let me go to the folder. So this is, can I hope you all can see the picture. Vishwa, can you confirm?
Hey.
No, we can just see the slideshow.
Okay. Let me just. How about now?
Yes, I can. We can.
Oh, okay. So this is the first telescope which I bought like some 5-6 years ago, and with this I was able to capture, not with any camera like DSLR camera, planetary camera, just with the mobile phone using afocal photography, just by holding the mobile phone on the top of the eyepiece and you can capture images something like this. Okay, can you see the moon image here? Kirti, Vishwa, can you see the image?
Yeah, we can see them.
Yeah,
Right. And I think
Wait.
Praveen,
Guys,
can you please mute?
please mute.
let me check who it is.
Yeah, Prabhu, I think you can continue.
Yeah, okay. So you can see the image of the moon, and you can see the chromatic aberration around the edges. That's because of the eyepiece which was used, as it is an eyepiece projection. And this was captured around February 2nd, 2015. And with the same telescope, you can capture a Jupiter, something like this. You can capture uh, the the image of Jupiter and also the moons of Jupiter. And then this is Sun. I was captured with the same telescope with the Mylar solar filter. You can see a few sunspots. Unfortunately, right now, Sun is not very active, so you won't be able to see any sunspots as it is in the minimum phase. And let me show you the video, like how it looks. This is a video of Jupiter captured with a mobile phone and hovered on the top of the eyepiece. So this is the basic setup, and with this you can do imaging something like this. Of course, I was not an experienced person at the time, so I was barely starting. So you could get better images than what I have. And then if you have a telescope, something like refractor, or if you have a reflector telescope like Dobsonian telescope, about 6-inch, 8-inch, 10-inch, you can produce some amazing results with that. So the first thing is choosing the equipment. If you don't have, you can buy one basic equipment. You can buy a basic telescope. With the binocular, you can do some sort of imaging, but you will get better results with a normal lens. I mean, camera and lens. So if you want to get a telescope, you can get a basic small refractor telescope, which is great. I would prefer a Skywatcher 90 millimeter refractor telescope with 900 millimeter focal length. That's an amazing equipment. You can get amazing results of moon and some planets as well. And next is the size of the aperture and the optical quality. So aperture size matters, and which we'll be seeing in the upcoming slides. And the next is collimation. You have to collimate your optics to get nice results, nice and sharp results. And then acclimation. You have to cool down your telescope mirror or lens to get the best out of it. And the next is focusing. You need to have a sharp focus of the image to get nice result. The next is seeing and transparency. So the sky condition should be good to get nice result. The next is sampling, to use uh, uh, a necessary sensor with respect to the telescope focal length or telescope. So if you don't use correct sensor size, then you will end up with either oversampling the image or undersampling the image. That is a kind of more detailed one, but we will cover it later. And the next is preparation of imaging. Like if you want to image, you need to prepare with the help of software to know. You need to know how high the planet is going to be and what time it's going to rise. And you need to plan the entire session. Next is image capturing, and then image processing and archiving the data, and then practicing with the available data, and also practicing it with the telescope in the upcoming days, so that by doing trial and error, you can learn a lot. So let's see each and every topic one by one. So like I said, choosing the equipment. So you need to choose the telescope, which I've already told you. And the next is the tracking mount. So for planetary astrophotography, and for any other astrophotography, you need to have a tracking mount, unless you're capturing some single exposure, like single shot images of moon or sun. You don't need a tracking mount. But to take videos of the planets, which I will be covering later, which is called lucky imaging. To get the best resolution of the image, you need to have a tracking mount. Otherwise, there are other alternatives, which I'll be telling you later as well. And the tracking mount, in the sense, if you have a tracker, a small tracker, if you have a small refracted telescope, you can load it on it. Otherwise, if you have an equatorial mount, which is big and sturdy, and the payload can be more, like 20 or 30 kg payload, you can mount a big telescope as well, and you can track and you can take videos of the planets and moon. If you don't have a tracking mount, if you have a Dobsonian telescope, let's say, you can get a tracking platform, equatorial platform, like the one that I have here. I'll share the video later, so that you can just load the Dobsonian telescope on it, and you can track the motion of the planet, and you can take a video and you can process it. The next thing is cameras. So there are different types of cameras. So in the past, like in the 1990s and all, so we didn't have these planetary cameras that we can have now, like CMOS, small sensor cameras. So at that time, they were using CCDs, and then amateur astrophotographers, or people who can't afford these CCDs, which are expensive. So they were able to get nice images with the help of webcam. So webcam is an inexpensive camera. If you don't have a budget to purchase a good planetary camera, you can start with webcam. After mobile camera, you can move on to webcam. Or if you have DSLR camera, you can do planetary photography with DSLR as well. So, and the next one is the planetary camera. So at this era, we have plenty of planetary cameras of different size of sensors with different configuration, where you can get best images. Even you can compare the photographs of the planets captured from Earth with a modest telescope can be comparable with the Hubble Space Telescope images as well. And next thing is adapters. So you need certain adapters to connect your camera with the telescope. Let's start with DSLR camera, since most of you own DSLR. So you need two types of adapters first. One is T-ring, telescope ring, and then another one is the T adapter. And there are few adapters which doesn't come with a Barlow, which is like a magnifier. So this is just a T adapter and a T-ring. So you can just connect these two, and you can attach it to a DSLR camera. I don't have the DSLR right now here, but you can attach it to a DSLR, and you can just put it on the top over here, just like this, and you can get the image. And the next thing is, you can capture moon or sun just by attaching without any Barlow lens. If you want to magnify it, you can attach the Barlow. Just a moment. That's Bixby. So you can attach. Yeah.
Hi, Prabhu. So actually, people are not able to see you. So can you switch from your desktop to your camera so that they can?
Sure. Forgot. Yeah. Is it visible now?
Yes.
Yeah. Sorry, I just forgot. So this is the T-ring, and this is the basic adapter that you need to connect your DSLR with your telescope. And this is the T adapter without a Barlow lens. So this is a typical T adapter which comes with a Barlow lens as well. So if you don't want to magnify the image, you can just remove this and you can attach these two, and then you can connect your DSLR and you can attach it over here. So I hope you can see. So that's where you have to attach. Right now I don't have the DSLR, so you can just imagine that that's how it attaches. There are some telescopes like GSO brand and other brands which doesn't have enough back focus, in focus, in the sense. So some telescopes are only meant for observation purpose. So the focus doesn't reach out. So if you put an eyepiece, let's say, if you have this eyepiece, if you put the eyepiece, the focus point is somewhere inside this. So when you put the eyepiece, the lens element touches that and gets the focus, and you can see the image. But when it comes to a camera, the DSLR sensor or any other sensor will be here. Since you're adding the adapter, so it won't go in, and that's the maximum end limit. So you cannot get the object in focus. So those kind of telescopes, most of the amateur reflector telescopes are of this kind, which doesn't have enough in focus. So what they would do is they would either move the mirror up, which is very difficult, and I wouldn't advise that for if you are a beginner. Otherwise, you can use a Barlow lens, such as this. So when you attach the Barlow, of course, the image will be magnified, but you can focus the image. So if you want to focus, if you want to capture moon as a full disk image, if you have a small reflector telescope, you can attach it and you can get the full disk. If you don't get the full disk, you can, if you have a full frame camera, because most of you might use a crop sensor camera. If you have a full frame camera, then you can get the full disk image. Even with the full disk image, if you're not getting a full frame, full disk image of the moon or sun, then you can take multiple images and you can stitch it. Like you can take panel by panel. Let's say I have a model moon here. So if you're not able to get the full disk, if the sensor is not covering the full disk, you can take panel by panel, like 1, 2, 3, 4, and you can stitch it everything together in Photoshop. So that's how I used to do with the 8-inch reflector telescope. And then other adapters, um, like if you have a 2-inch focuser like this, you may need to have a 1.25-inch converter like this to attach this. Otherwise, you won't be able to connect the telescope. But most of the telescopes out there, it comes with both 2-inch and 1.25-inch. But some amateur telescope, it doesn't come with 2-inch. It just comes directly with the 1.25-inch. So let me get back to the presentation. So I hope you can see the slide. So the next thing is the Barlow and extender. Like I said, there are difference between Barlow and extender. Barlow, it has two elements inside, and it magnifies the object. And depending on the position of the sensor or the height of the sensor from the Barlow lens, the magnification changes. For example, if you're using a 2x Barlow, it magnifies the object 2 times. And if you keep the sensor away from the Barlow, then the magnification can increase from 2 times to 3 times, perhaps 4 times as well. So this has some disadvantages. So since it is increasing beyond the limit, so you don't get a sharp image. So it would be rather fuzzy, and there will be light loss around. So you won't get a sharp result. And also there are other disadvantages as well. So to get rid of this, there is another thing called extender. So here, the one that I have is an extender. So this is not like a Barlow, and there are some expensive extenders, expensive multipliers such as TeleView brand. You must have heard about TeleView PowerMate, like 1.2, 2.5x, 3x, and 4x and 5x. Those are pretty expensive. The cost of those PowerMates are similar to any beginner telescope. It costs like 30,000 Indian rupees. But this one is something affordable. This is Explore Scientific brand, and this is a 3x extender. So unlike Barlow, this doesn't increase the magnification irrespective of the sensor. So no matter wherever you keep the sensor, even you can keep the sensor here or here by using another extender, doesn't matter. But the magnification remains the same. It will be always 3 times. It will not increase to 3, 4 times or 5 times. And this is what we call as parafocal. And also, there won't be any light loss, since there won't be any increase in magnification. There won't be any light loss. The image stays sharper. The best extender, best multiplier is you can keep the eyepiece without any extender, and you can see the object through your eye, and you can just remember the sharpness and you can remember the brightness. Now I had a multiplier like Barlow or PowerMate or Tele extender, and you should not see a light loss. It should be the same, but with increased magnification. When you have such kind of extender or Barlow, that's the perfect one. But those kind of things are pretty expensive, like I said. And the next thing is eyepiece projection. So, like I said, eyepiece projection is something the best way to start with. So, for the eyepiece projection, you can either hover the mobile just like this on the top of the eyepiece, and you can hold it and you can get the image. So if you don't have steady hands, or if it is windy, if you want to take a video for the planets, you can use an adapter, something like this. So this is a mobile adapter, and this is for your mobile. You can connect it here. I hope you can see. And this one is for the eyepiece. So here you have to add this, and then you have to attach this. Just like this. So when you have this adapter, then you have an opportunity to hold it for a longer time, and then just connect it over here. And then you can shoot it without holding it. So you can just open the camera and you can take videos, you can take photos, and also you can use this adapter for any celestial event as well, like eclipses. You can use this, and it gives you a pretty good result. So the next thing is filters. So there are some filters which are very good for imaging and also for observation. So you must have heard about filters like red filter, green filter, blue filter. For specific planets, you use specific type of filter. For example, when you use blue filter for the Mars, you can see the polarized caps, and you can use red filter and also blue filter for Jupiter and Saturn for observation. In the same way, you can use different color filters, but if you are using a monochrome camera, like a black and white camera, you can use those filters to get red, blue, and green color images, and you can merge all the colors to get a nice image. But there are other filters apart from these color filters which you can use for the planets. Like these are, you can say, not beginner level planetary photography, but you can say the next level. So I have few filters. You can one of the majority of the filter, most of the astrophotographers that you use is infrared. So this is an infrared filter, and the wavelength of this is 685 nanometer. So this one is close, it's to the far end of the red spectrum. And the reason that we use this and other infrared filters, because our Earth has atmosphere, and when when a light from the object, like planets, when it enters, so it disturbs it. So it's like it makes a zigzag pattern, and when you look at through the eyepiece, you will see the object. It makes fuzzy, and it creates a wave or ripple kind of thing in the atmosphere. So you won't see the object very well in the normal visible light. But the longer wavelength, which is red, which is less susceptible to the atmosphere, so you can see it sharper. So it doesn't affect the red spectrum much than the other spectrum, so you can see it clearly. So when you use infrared filter for imaging the planets and moon, you can get nice and sharp image than with a normal colored filter. And there is other filter which is very useful, which is called infrared and UV cut filter. So when you use a planetary camera like this is more sensitive to both infrared and ultraviolet other than the normal colors. So it is sensitive in both the ends. So since it is sensitive throughout the spectrum, when you capture any planet, it doesn't only capture normal color, it also captures infrared. And the infrared wavelength, it focuses at a different distance. So it makes it more fuzzy. So when you capture a color image of a planet, let's say Jupiter, when you don't use this filter, you will also capture infrared light, which makes it more fuzzy. So when you add this with the camera, then it cuts that infrared or ultraviolet end of the spectrum, and it gives you a nice and sharp image. So this is mandatory for planetary photography and also for moon. And there are other filters such as this. This is called 850, infrared 850. So this is much into infrared than the 685, but since it is more towards the infrared spectrum, so the resolution becomes less as well. But you'll get some nice and sharp image, but the resolution with the expense of resolution. The next is methane filter, and this is a methane filter. Its wavelength is something around 890 nanometer. So this is way beyond, and it gives you very dull image because since it is not close to the any of the like red spectrum, so it's all the way towards the end of the red and beginning of infrared. So it gives you a dull image, but when you capture Jupiter and Saturn, you can see the entire planet in a completely different view. I'll show the image later. And then you have some color filters. Like I said, you can use blue and violet color filters for Venus. And when you capture or when you see Venus visually without any filters, you won't see any details because the cloud structures you cannot see it. And only if you use ultraviolet or violet filter, you can somewhat capture the cloud details, particularly in the ultraviolet, because the cloud details, the higher and lower clouds, are very much visible in the ultraviolet spectrum. So it gives off energy in that spectrum, so you can see it clearly, and you can see the cloud details with these kind of filters. But you need to couple this with other kind of filters like infrared, cut off the other spectrum. Otherwise, the other spectrum will also leak into the image, so it will make it more fuzzy. And the next thing is atmospheric dispersion corrector. So most of the problem that we have is most of the planets, particularly Jupiter, Saturn, these will be very low on the horizon. Even when it reaches the highest point, when it crosses the meridian, it won't be higher than, let's say, 50 degree from India, let's say from 10 degree or 13 degree north. And as you move higher in the latitude, so the object goes more lower and lower. So since the object doesn't rise high up, you need to cancel out the atmospheric dispersion. So you must have noticed, particularly while seeing Venus, when you see the Venus when it is low on the horizon, you would notice some colors like red and blue, both on the top and the bottom. So that is because of the atmosphere. So I have a picture of the atmospheric dispersion. Let me show it. Yeah. So here in this image, Kitty, can you see the image?
Yeah, we can.
Right. So here, this is an image uh, of a moon, I believe. So you can see the blue and red color. So this is because of the atmosphere. Like I said, our atmosphere acts like a prism. So it diffracts the light, and it gives you these different colors just like a prism. But when you add an atmospheric dispersion corrector, so this corrects that dispersion. So there are few prisms like wedge-shaped prisms which will change its position, and it will show you the corrected image. And when you use this corrector, you will get a nice and sharp image. I'll show the corrector that I have. So hope you can see. So this is an atmospheric dispersion corrector, and to use this, there is a manual which you can see it later on. So you just need to adjust these two knobs. So there are two prisms. By turning these like back and forth, you can cancel out the atmospheric dispersion. And this is not very expensive. You can use this if you are using a big telescope. And then the next thing is laptop and PC. So I'll just share the screen. So the next thing is a laptop and PC. So when you're using a planetary camera or a web camera, you need a laptop or a computer. Only for DSLR, you don't need a camera. And when you use webcam and planetary camera, you need a laptop which has more RAM and which has more space in it, because videos of these planets, it occupies a lot of space. One video can take almost like 20 to 30 GB of space. So in one session, if you're imaging 4 to 5 planets, then you will end up with 200 GBs of data. And if you don't have enough space, then you might want to delete some of the files, which you will find it nice. So you need to have always enough space. I would suggest to carry a hard disk if you don't have enough space, so that you can directly capture the data in the hard drive. But there are a few more tricks which you can use. When you're using planetary camera, you're gonna capture a lot of frames in the video. I'll cover the video taking the video, which is lucky imaging technique, in the later slide. But just to give you an idea, so for the planets, we take videos, and the videos should have more number of frames, so that we can cancel out the unwanted frames which are not good because of the atmosphere. So to pick out those frames, we need fast cameras, like which has a lot of frames per second, like 100 to 200 frames per second. So in less time, you can have more data. So to have fast frames per second, you need to have fast machine, like laptop which has 8 GB of RAM or 16 GB of RAM, and with solid state drive. Solid state drive is one of the important thing if you have a laptop, if you want to capture more frames per second, like the one that I have here. Yeah, so this is 500 GB solid state drive, and when you capture the image with this, it can give you frames per second, which is around like 300 frames per second. You can take maximum of 300 frames per second with this 500 GB. If you don't use this, if you use only hard disk drive, then you will end up with half of it, like 150 frames per second. So if you have a planetary camera, I would suggest use a solid state drive to get more frames out of it. And then if you don't have a fast laptop, or if you have a laptop such as, let's say, 2 GB of RAM or 3 GB of RAM, I would suggest you to close all the application, only use the image capturing software. You can get something out of it. And also, to increase the frames per second, we can also crop the portion of the imaging. Like if you're capturing Jupiter, you don't need the remaining portion. You don't need the background space. Just need the planet. So you can crop the planet, and you can fit the field of view into only that planet, so you can get more frames per second. I'll be covering that later as well. And the next thing is the software. So there are different types of software which we use for different purposes. I'll just show you a few that I have. I'm not able to show my desktop. Okay. Can you see the desktop here?
Yes, we can see
Right. So there are few softwares which are necessary for planetary imaging. If you're using both DSLR or webcam or planetary camera, the first thing is image capturing software. There are two softwares which are good, which are free. One is Fire Capture. So this is Fire Capture, and then the other one is SharpCap. So these two are free softwares where you can take uh, videos of the planets. Just a moment. Yeah. So here you can see the Fire Capture, and this is just a dummy image of Jupiter with one of the moon and its shadow. So here on the left hand, you can notice rate of interest. So that's what I was talking about. So let's say my camera's resolution is HD, like 1920 by 1080 pixel, and the Jupiter is covering only 500 by 500 pixel. So you don't need the rest of the things. So you can reduce the rate of interest here by changing the value. So you can only get the Jupiter. And then down here you will have gain. That is similar to ISO in the cameras, in the DSLR cameras. So here you can increase and decrease the gain, but don't increase the gain too much so that you will end up with a lot of noisy image. Then the exposure is more like a shutter speed. So here, depending on the brightness of the object, you can change it. For Venus, you can keep always lower value because it is too bright. Even when you use Barlow or extender, it's still too bright. And then for the moon as well, for the sun as well, it is too bright. And for the moon, if you're capturing like high definition, high resolution images, when you use Barlows, then it becomes dull. So in that case, you need to increase the exposure. And for Jupiter, it is kind of bright when it is at the opposition. And Saturn, its surface brightness is lower than Jupiter. So for Saturn, comparing to Jupiter, you might want to increase the exposure. And then don't need to touch anything in gamma. And then down here, you have the planet type, Jupiter, Mars. So if you're capturing Jupiter, you can just set Jupiter, and it will set the files accordingly. And if you're capturing Mars, you can change it to Mars. And then when you click this play button, it will start capturing the data. And if you're not using tracking platform or tracking mount, then you have to manually hold the telescope to move it. So I'll show you how I used to do it. So when I didn't have the EQ platform, hope you can see it. So I was just using the this one, the finder scope. Let me just move it this way because that's it. It's not. Kitty, can you see the telescope?
Yes, we can see it.
Yeah. So you can just look at the object through the viewfinder and make sure your viewfinder and then the telescope is aligned, and make sure that you get the object at the center of the crosshair, and at the same time you get the object at the center of the field of view in your camera or your eyepiece. And then when you look at it, you have to track the object manually with both your hands. So you can keep one of your hand here and other hand, right hand, at the back, and you can, just by looking at it, you can move it up, down, left, right. This is called altitude and azimuth motion. Just because since it doesn't have a tracking mount, you have to move it in this way. And when you track it in this way, you will also have other problem, which is called field rotation. When you're taking a long video, then you will have the field rotation where the object moves as well. It rotates. That's because of this altitude azimuth movement. And when you track the object with the tracking mount, then you will not have that field rotation. So you don't need to correct that error later on for the post-processing. So this will be very handy for this if you don't have a tracking mount. Let me get back to the software. Yeah. And then here you can see the histogram, and then here you can see the temperature, and you can see the file. So here you can change the file. I always keep it in AVI, and you can keep it in SCR file as well. So in this software, there is another important thing. Here it centers the frame automatically. So you don't need another software to center it. So without any need of other software, it automatically centers the object at the center. I haven't connected the video, the camera, so I won't be able to show how to center it. Probably I'll show it later. Yeah, auto align. So you see there are 4 dots. So when you click this auto align, then it aligns it automatically at the center. So it won't wobble left and right, up and down, unless you're keeping the target within the field of view. So this software is very handy, and there is other software which I always use, which is SharpCap. So this is also a free software, but there are other options where you can use it for deep sky as well, but you need to get a license to get the pro version. But this is easier than the file capture. So here I have a simulator test camera. Yeah, let me get high speed. Yeah. So this one is a simulator of a planet. So here on the top left you have settings. The first and foremost thing, if you are capturing a video, is you need to change the settings. You need to change the file name. You need to enable the date and universal time, because this will be useful later for post processing. So always go to the file names and make sure you have this data. So the file name should end up with the universal time with the date, this format. And then if you're having a solid state drive or external hard disk drive, you need to change the location of the image or the video. So here you can choose, and you can let's say if I have this hard disk drive, I can just choose this as a destination. And also you can check the speed of your laptop with the camera attached, so you'll have an idea how fast it's going to record. And the rest of the things you don't need. So the next thing that I would like to show is to the right hand side, you have a panel. So similar to file capture, you have capture area. This is the rate of interest, which I was talking about. And then this is the camera type. If you're using a color camera, make sure that you enable this. And then this one, gamma and gain, and then the exposure. So here you have to consider only on these two, gain and exposure. Similar to file capture. And then here you can see the histogram, and here you can capture the video. And there is one trick that you can use if you want to have fast frames per second. Make sure that you capture it in raw file. So here it's not showing now. Let me just attach the camera so I can show it right away. When you capture it in raw, you have more frames per second, and there won't be any loss. Sometimes frames, there will be loss in number of frames because of various factors, because of the compression from raw file to the color file. So let me just connect it here. Yeah, so when you connect it, it will show you the name of the file, name of the camera. Here it shows the W290MC. And here it will show you raw 8. So if you have this, you won't have any drop. Here it shows only 2 drop. If you can see the bottom left, you can see previewing, and you can see the number of frames, and then in the bracket you can see 2 dropped. And then next you can see the duration, and then you can see the frames per second. So here frames per second is 170 FPS. So when you increase the exposure, you will see the frames per second, it decreases. Now it's around 60 FPS. But if you want to have the same brightness, you can decrease the exposure and you can increase the gain. So you can compensate in that, but with the expense of some noise. See, so here you have same 170 FPS, and if you want to get more, you can try reducing the exposure and increasing the gain. But even if you increase the exposure beyond that, you will notice that it will not reduce further, because that's the maximum limit for this camera. So since it is not going to reduce further, so you can keep the value, you can keep the exposure higher, and you can reduce the gain if you know that limit, so that you will have a nice and smooth image. And now I'm going to reduce the capture area, which is rate of interest. Right now I have 1936 by 1096. Now you will notice suddenly the frames per second will increase when I move to 800 by 800. So I've changed it, and you can see the rate of interest, it becomes a square. Before it was a rectangle, and here now we can notice the frames per second, it has increased to 225. And if I decrease the rate of interest further down, you can see the frame per second also increases. And when I decrease the exposure, you will see it goes 500, 600, and 650 is the maximum. So this frame, this rate of interest is good for smaller planets. Like right now, Mars is pretty far away, and for Uranus and Neptune, you can use this. It's depending on your telescope focal length. So now I will change the color speed from raw to RGB. You will notice the frames will be dropping. Here in the bracket, now you can see it's 22 dropped, 24 dropped, and it keeps increasing. So when you keep raw, you will not have any frame loss. So you will have all the frames that you're capturing. So this is a trick that you can use. And also you can have quick capture. So if you want to capture, on the top left, you have start capture. And then here you have single frame, unlimited number of frames. So if you know the number of frames you want to capture, you can just set up the number of frames. If you want to capture according to the duration with respect to the planets, because all the planets, it rotates in on itself. Like Saturn and Jupiter takes roughly 10 hours, and 9 hours, like 56 minutes for Jupiter, and Saturn 10 hours, a few more minutes more than Saturn. So for these planets, you need to limit the duration. Otherwise, you will have a blurred image of the planet. If we capture the video of these planets more than, let's say, 3 or 4 minutes, then you will not have a nice and sharp image, because since by the time you finish the recording, the planet would have moved, and when you post process it, you will have a fuzzy image because of the rotation. And for the planets which are slowly rotating, you can set the time limit far beyond. I will show the exact numbers in the upcoming slide. So this is the software, and these two are the image processing, image capturing software. And once you're done with capturing, and there are other softwares to process it. So I'm not going to open it. I'll just show you what are the other softwares. So the first thing is Auto Stack It. So this is a wonderful software to stack unlimited number of videos in one go. Earlier, we were using Registax. So Registax is limited to the number of video files. It cannot do batch processing. And also earlier, the CPU limit was lower. And so even to process one video, it took longer time. But with AutoStackit, you can load like 15, 20 images, videos, that you can batch process everything. So nowadays we use processing. For stacking, we use AutoStackit, and for sharpening the file, we use Registax. These two are the processing softwares. And also you can use Photoshop or any other platform later on for post-processing. So now let's get back to the presentation. Yep. Can you see the slide, Kirti?
Yes, we can see the slide.
And the next thing is aperture and optical quality. So aperture size matters. If you have a small telescope, you will not have much details. If you have a big telescope, you can have more details. So depending on the size of the telescope, the result differs. And also depending on the place, also it differs. And the next is optical quality. If the mirror or the lens is not perfect, if the mirror is not grinded very well, then it affects the quality as well. So whenever you purchase a telescope, make sure your mirror and the entire equipment is in working condition, everything is good. And the next is central obstruction. This is a common problem with the reflector telescopes, also other kind of telescope like Schmidt-Cassegrain and Ritchie-Chrétien. So you have the secondary mirror at the center, which obstructs the primary mirror. Because of that central obstruction, you have loss in contrast. So depending on the size of the secondary mirror, the contrast loss differs. For example, for my telescope, the secondary camera size is 88 millimeter, and then the primary mirror size is 406 millimeter. So the loss is around 21 percentage. So contrast loss is 21 percentage, and this is good for reflector telescope because the secondary size is smaller. And for other kind of telescope like Schmidt-Cassegrain and Ritchie-Crichton, so it has bigger secondary mirror, and the contrast loss is beyond 30 percentage. So if we compare, let's say, 14-inch Schmidt-Cassegrain image with 30 percentage central obstruction, and if you compare a 10-inch telescope without no obstruction, you would find very less difference because of the central obstruction. And then the next thing is open truss and strut design. There are telescopes, particularly Dobsonian telescopes. You will see some truss, like you will see 6 poles which holds the primary and the secondary mirror, the upper tube assembly and the lower tube assembly. So together we call it as OTA. So there you need to cover the opening, otherwise you will end up with loss of contrast. And also it's the same for strut design. For example, my telescope is a strut design, so it has only 3 poles which holds the telescope, and I had to create 3 more poles to keep it in between the struts to cover it completely with the light shroud. So here, let me just stop the screen. So I hope you can see it. So this is what I'm talking about. Let me just remove it. So you can see this is a strut design, and the other design is a more common one. So here you have some issues because it doesn't hold the upper tube assembly properly. And when you add this, then you can protect the primary mirror from dust and also from light loss. So it is a major thing if you're doing the imaging in a light polluted area. If you're capturing moon or planets, you need to have some clothes to cover the opening. And also it'll be helpful during winter as well. It will protect from dewing as well. And then the next thing is the light shroud. Yeah, so I have covered it. Light shroud is very important if you have an open telescope model. And the next thing is collimation. So collimation is one of the major thing before you do anything. So you need to collimate your primary with the secondary properly. And there are a few tools which we can use. So I have 2 tools, and before that let me show you the normal way. So if you don't have any of these tools, you can just use your eye, and you can just keep your eye through this eyepiece, through this eyepiece holder, and you can see at the center of the primary mirror there is a hole at the center, and then you need to align that hole with respect to your pupil. So this is more a typical way, but it's not the accurate way. So when you can look through this, when the light falls through this opening, you can see your pupil at the secondary mirror, and also you can see your pupil at the center of this primary mirror circle. If you don't see the circle at the center, then you can move this and that, you can align it center. But this is not the accurate way. The more accurate way is by using some tools like this. This is a laser collimator. This is for reflector telescopes, and for Schmidt-Cassegrain telescope, you can just look at the star or the object by defocusing it. You can see the airy pattern or diffraction rings around, and by looking at the concentric rings with respect to the central one, you can change the collimation. So that's more easier way. But for the Newtonian telescope like this, you need to keep this laser pointer collimation tool, where you can see there is a white color panel which is kept at the diagonal, and then you can see the a laser light which is coming through this, and you can also reduce and increase the intensity of the laser light. All you have to do is just keep your laser light, the collimation tool, over here, and make sure you keep it tight, because some of the telescope comes with a focuser like this, and some of the telescope comes with a normal focuser. And when you have a focuser like this, like 10:1 Crayford focuser, there are two knobs. I hope you can see it. Can you see the detail of the focuser, or should I move the laptop closer? Kiti?
You have to move it closer.
What if I use my mobile and show it?
Yeah, that would be better, I think.
Let me just open it here. Just few minutes, folks. Can you see it?
No, we still see your, I think, laptop camera.
Okay, let me just change it.
Yeah, we see it in another window.
Yeah, that's what I'm trying to. I'm trying to show that window. I've changed the host.
Prabhu, you can mute your laptop.
No, I've muted this, so it won't. You won't listen the audio from this. Is it visible with that the bottom window, or should I change?
If you mute your laptop, the bottom one will become primary.
Okay, I'll do one thing. I'll just take the laptop and I'll show it there. Yep. Is it visible now?
Yeah.
Okay, so you have two knobs here. The first one, this controls the tension of the focuser. You can see I'm just moving it back and forth, and it has two speeds. So this one is more finer speed, and this is faster one. So with this, you can fine tune the focus very well. And this one, the bottom knob, this one locks the focus. So when you adjust this tension knob, make sure the focus doesn't shift here, because when you tighten it here, you will see the entire image will move either to the left or right because of the tension here. So the light coming from the secondary, it comes directly here, and when this portion is not perfectly aligned, then you will end up with poor collimation. So before collimating it, make sure everything is firm. And next thing is, you will see the primary the laser light which is falling over here. Can you see the red laser at the center of the primary mirror?
You need to tilt your laptop a little bit.
Okay. What now?
Barely visible. Barely visible. Yeah.
Barely visible.
Yeah.
Okay. And then that light, it hits the secondary, and here you can see the laser over here. So it exactly falling at the center of the hole. So if in this case it's perfectly aligned. So let me just loosen the knobs, the collimation knobs, and you will notice it shifts. So here it's not exactly at the center. So it has moved to the bottom right, which means it's not perfectly collimated. So in this case, you will have poor output. So collimation is very important when it comes to planetary photography. So these are the tools. So the other one, apart from the laser collimation, there is other one which is called Cheshire eyepiece. So this is another collimation tool. It's same like this, but here you will have to collimate it by looking through it, not with any laser. So here you will see a crosshair, and when you look through this, you will see the primary and the secondary reflection, and everything has to align automatically. And I have to show pictures in order to show you everything, but I don't have those pictures. So just take it as an example of how to collimate. There are more detailed explanations required to collimate, because you have to adjust the primary mirror and secondary mirror, and it's a complete it's entirely a different video, so we'll cover it maybe later. But for planetary, you need to have a good collimation. And then the next thing, just a moment. Next is acclimation. So acclimation is nothing but like keeping your telescope at thermal equilibrium. When you are traveling from one location to other location, let's say you're taking the telescope to a dark site and you keep it in your car, and when you take your telescope out, the temperature of that will be different. Or if you're keeping your telescope inside your house, and in the summer when you take it to the terrace, the temperature of your mirror and the outside temperature is different. So when you have a temperature difference, then it affects the seeing. So it's same like when you look at the object when it is low on the horizon, you will see it makes this waves and ripples because of bad seeing. So exactly the same view you will get if your mirror is not acclimated. So thermal equilibrium is more important. What you can do is you can reduce the temperature of your primary mirror by using fans. So some telescopes, some big telescopes has external fans, and when you turn on the fan, then it reduces the temperature. The heat radiates away. If you don't have this fan, what happens is when you keep the telescope out, then outside temperature is more lower than the mirror's temperature. Then it takes many hours to radiate the energy. So when the heat waves radiates, so it affects the light which is going through the mirrors, and you will have this wobbling effect, all the waves and ripples because of the heat waves. And if you can take the temperature from beneath by keeping a fan, if you don't have an external fan, you can keep some other fans, like you can keep the table fan and beneath that, and you can use it as a ventilator as well. So in that way you can cool it down. If you don't have any fans, the only way is to keep the mirror outside for a longer period of time until it acclimates. Like it could take an hour, 2 hours, perhaps 3 to 4 hours as well, depending on the temperature difference. So what you can do is to make sure that it is acclimatized. So you can use a sensor like this, infrared thermometer. You can use this, and then you can just point it towards the primary mirror, and you can check the temperature of it. So here it will show you. I'm sure many of you must be familiar with the present situation. So here it will show you the temperature of the primary mirror, and then you can use the same thermometer outside. You can check the outside temperature, the ambient temperature, and you can see the difference. Then let it cool until it equals to the outside temperature, and then you can begin the session. So it is helpful for both observation and as well as astrophotography as well. And there are other types other methods where we can reduce the temperature by keeping insulators like aluminum sheets outside. So those are some complicated procedure for more in-depth imaging. So let's keep it simple. That you just need to cool down your mirror with the fan. And then the next thing is focusing. So like I said, focusing can be changed over the time because of temperature difference, particularly for refractors. The focusing distance, it also differs over the course of time. If the temperature is hot, then you will have a focus at one certain point. When the temperature cools down, you will have a focus at another point. So you need to check the focus during every imaging, like at least 30 minutes once. You can check the focus and you can adjust it. So there are ways where you can adjust the focus. You can either point towards a star and you can just move the focuser wheel back and forth and make sure that it is very sharp. Or if you're using a reflected telescope, you have the spider veins, like the cross, which holds a secondary mirror. So you will see that you will see eight veins when you look through it, if it is not focused, because of the mismatch. And when the eight veins aligns with 4, then you will have a perfect focus. That is another way of fine-tuning the focus. Or you can point it towards the planets or moon if it is visible, and you can use higher IPs, and you can change the focus, and you can check the details of the surface. If you see sharp and nice and smooth surface, then it is perfectly focused. So there are tricks that you can use. You can either use the fast rotating focuser wheel, or the slowly rotating focuser wheel. But always use fast rotating focuser wheel to judge how good the focus is. And then once you get close to that sweet spot, then you can use the slow rotating focuser wheel to fine tune it. And then other thing is using motorized focuser. So if you can afford, if you can get a motorized focuser, you can attach it and you can check the focus with the help of the laptop, and you can just change the focus. The reason is, when you touch the focus wheel, you will have wobbles, because you're particularly when you're magnified so much with the planetary. If you're using a 3 times Barlow, it will be magnified so much that you will only see the planet within the field of view. When you make slight touch, it will wobble a lot, and you won't be able to judge the focus. You need to have a sturdy and clear view to judge how good the focus is. If it is not sturdy, then you will end up with bad judging. So it is very important to have a sturdy image to see the focus. So if you can afford, if you can get the motorized focuser, then it will be really helpful. And the next thing is seeing and transparency. Can you see my screen?
Not yet.
Just a moment. Yeah, can you see the screen now?
Okay.
So seeing and transparency, before any other thing, these are the important things, particularly seeing. With bad seeing, you will end up with bad image, you will end up with bad result. So capture when the seeing and transparency is good. I'll show a few examples so we'll have a clear understanding. So this image, can you see the image of Saturn?
Yes, we can.
So this is an image of Saturn captured by one of the ace astrophotographer, Damien Peach. So on the left-hand side, you can see the airy disk. So the first image, it shows nice and smooth concentric circles. So that indicates very good seeing. It's excellent seeing, and you will have a sharp image like the right-hand side. And all the way to the bottom, you can see the airy disk. It's not very well defined. So you will have waves and the arcs, and you won't see any concentric circles at the edge. So it merges together. So in that case, you will end up with bad image. So also it reduces the resolution of the telescope. Like I said, the result of the bottom Saturn is equivalent to a telescope captured with a small telescope under best seeing. So if you don't have best seeing, if you capture the images with bad seeing, then you will end up with poor image. And also, to identify how good the seeing is going to be, you can use some apps. You can find the weather. So meteorology is important to do planetary and also deep sky imaging to understand how weather works. So when you see cumulus clouds like this, because there are different types of clouds in the atmosphere, like cirrus, cumulus. So when you see cumulus clouds like this, then the seeing is going to be good, because these are low-lying clouds. Sorry, seeing is going to be bad. I'm saying the other way around. So when you see cirrus clouds, which are high clouds, then you can say that seeing is going to be average or good. It's not going to be bad. So you can check in the afternoon and you can judge how bad the seeing is going to be. And also to understand how seeing affects the viewing. So here on this left-hand side image, you can see normal state of temperature. So in the daytime, our Earth stores the heat from the sun, and in the nighttime, it radiates away. So very close to the ground, like 0 to 200 meters, you have warm air from the Earth, which is being radiated to space. And the top, you have cool air. And when you have this temperature difference, when it's going to mix with that, then you're going to end up with very bad seeing. And on the opposite side, you have temperature inversion, and the bottom is cool and the top is warm. So here, the seeing is going to be good. And also, there are other techniques where you can learn how bad the seeing is going to be. Before talking about this image, I'll just share a few more information. Seeing is always good if you are imaging very close to the ocean, close to the seashore, because near the seashore you will have air, cool air, and if you're in a polluted area, like in a civilized, like you have a lot of buildings around, then human-made sources gonna radiate a lot of source than the Earth. So you will have too many heat sources, which affects the seeing. So near the shore area, the air is cooler, and you will have best seeing. And also on the top of mountain, you have best seeing. So these two are the areas where you can get excellent seeing and you can produce excellent images. And also, when you have a rain, it clears all the dust particles in the atmosphere. So the transparency is also very clear. So in order to understand transparency and seeing, I can give you an example. Like, let's say you can see the stream of water in this image. Can you? There are two images.
Yes, we can.
So the top image, you can see the rocks and pebbles under the stream of water, and the bottom image you cannot. So the bottom image was captured in a single shot, and the top image was captured by with a video with a video file, and then it has been transformed to a picture by reducing the effects of the stream. So here you can see the pebbles very clearly under the water. So let's say if I put a coin under the water and the water is very clear, and if I pour some milk into the water, then you will not see the coin clearly. That means the transparency is not good. In a similar way, when you look at the objects with the telescope, the dust and other things in our atmosphere makes the transparency poor. So after rain, it clears everything and the transparency is great. And then the seeing is the stream of the river. Let's say when the coin is inside, if I make a ripple, if I put a stone around the corner, you will see the ripples. So you won't see the coin clearly. You will see the coin like it bends, it gets bent because of the waves. So these are the two examples which you can compare with seeing and transparency for the planetary imaging. So this picture was captured by one of an astrophotographer and my friend Neil. So this shows how effective the lucky imaging technique is, which I'll be showing you in a while. So I hope you got seeing and transparency. The next is sampling. So sampling is a kind of, it's not for beginners, but you can get an idea. So our sky is like, you can see 360-degree of the portion, and 360-degree is divided into minutes. 1 degree is divided into minutes of arc, and then 1 arc minute is divided into arc seconds. So Jupiter is, let's say, 49 arc seconds. That's the size of the object that you can see from Earth as seen through the telescope. So Jupiter's size is 49 arc seconds out of 360 degree. So if we can split it down. So each camera has pixel size. So it has the sensor size, and the pixel size. So there are cameras where the pixel size is around 2.9 microns. For example, my planetary camera is 2.9 microns. There are cameras which are 3.5 microns. So this is the size of the pixel. And when you add this camera to the telescope, so each pixel occupies data of object. Let's say the crater, the moon's crater, which you can see here. So if the pixel size is going to be smaller than the object that you're going to capture, then it's not going to sample very well. You're not going to get the details of it. Let's keep it in that way. Let's keep it simple. And if the pixel size is bigger than the object that you're going to capture, then in that way also it's not going to be very effective. So it would either undersample or oversample. So to match the sensor and the focal length of your telescope with the object, so there are a few formulas, but rule of thumb, you can maintain this. So the focal ratio of your telescope and pixel size multiplied by 3.5 times for the night of bad seeing. So when you have bad seeing, you can use this value. So if you're using let's say a web camera or a planetary camera or a digital camera, so you can find the size of the pixel in the internet, and you can add that value with this, and you can find out the effective focal length, effective focal ratio. And then the same goes to the good seeing as well. You can multiply it by 5 times. So there is other technique you can use, how good or bad the seeing is going to be. Always before setting up the telescope in the evening time. So in the daytime you can see the clouds. If there are no clouds, and in the nighttime, before setting up the telescope, if you have a binocular or if you have small telescope, just put it in and put some higher focal length eyepiece, and you can see how much wobble it gets. If it's going to wobble too much, then it's not worth trying imaging that night. If you can see if it changes over the time, then you can wait, because in over the night you will get some duration of good seeing and some duration of bad seeing. So always wait for the good seeing and you can capture it. The next is preparation. So you have to take care about the location.
Prabhu,
Yeah.
we have around 2 minutes more. Just wanted
Yeah.
to give it.
Yeah. So the next thing is preparation. Always prepare your location. Like I said, near the shore area, it's very good. And also make sure that you don't keep it on any surface which radiates the stored heat, like on a concrete wall or on a concrete floor. You will have a lot of radiation radiating to the space. If you are on a grass surface, so that's good. So you can always keep the telescope something like that, so it doesn't radiate the heat, and it won't affect the temperature of the primary mirror as well. And then waiting for the right time. Always wait for the planet till it rises higher. So there is no point of capturing it if it is lower. So you're not going to end up with the good data. So you have to plan your observation or photography by looking through the softwares like Stellarium, which is a free desktop software, or some mobile apps, and see when it is going to rise higher, and wait for the timing, and you can capture it. And also it's good time to capture the planets during the opposition, when the planets are aligned perfectly opposite to the sun with respect to the Earth. So every year you will have opposition. So this time Jupiter and Saturn opposition, they are very close to each other, and by the end of the month there is one of a lifetime event where you're going to see Saturn and Jupiter very close to each other. You can see it in one field of view. That's going to be a memorable event. So during opposition you can get the object very well, because it'll be closer first of all, so it appears bigger, and then it is properly illuminated by the sun. So you get the best out of the most. And then next is planning the targets with software. So you have to use softwares and to find how the planet is going to be. For example, if you're capturing Jupiter, there will be some eclipse events which will be happening, like the moons of Jupiter, like Ganymede, Io. It transits in front of it. It creates a shadow, and also like great red spot on the Jupiter. So it comes to the vicinity once in a while. So those kind of events you have to predict. You have to see the software, and you have to find out the timing and wait for the time, and you can capture. So don't miss out those opportunities. And cool down the OTA, yeah, that I have covered. So image capturing, so lucky imaging is the technique that we are using. So instead of taking single capture, because it doesn't capture much of the detail, by taking a video, so it captures all the frames. So let's say if you're capturing a video, you have 50% of the frames with good seeing and 50% of bad seeing. So with this video, we can remove the bad seeing images in the software, and you can only stack the good seeing images, and you can get the best picture out of it. And then with the DSLR, since the DSLR pixel size is bigger, so always smaller pixels, I mean smaller size of the sensor produce good planetary images than the bigger size. So optimal size of the sensor should be small for planetary imaging. So these DSLRs has bigger pixels, and it doesn't cover much of the portion. So you have to use extenders or Barlows to increase the magnification. But in DSLR, when you take a video of it, it changes from a 4K quality to HD quality. And you can capture only like 30 frames per second or so. But if you have cameras like 600D or 700D, you can use digital crop, like 1.5 times you can crop it digitally, and you can get the best out of it. So if you're using DSLR, always use inbuilt 1.5x cropping factor, and also with the Barlows or extenders. And then the capturing software, we have covered fire capture and sharp cap, and focusing we have covered. Framing rate of interest, we have covered. Exposure and gain, capture duration. Like I said, capture duration is very important. Mercury is not limited because it takes longer, I believe 58 days, and Venus, it's also longer, unless you're capturing the clouds. If you're using UV filter or infrared filter to capture the clouds of Venus, then you have to limit the time duration. Otherwise, you will have a blurred image, like to few minutes, because clouds moves faster than the planets. So you have to limit the time for Venus. And then Mars, it differs depending on the position. If the planet is farther, then it could extend all the way to 4 minutes. If the planet is closer during the opposition, then you have to limit the time to 1.5 to 2 minutes. Otherwise, you will have a blurred image. The next is Jupiter, is 45 seconds. So you can also increase it to 60, sometimes 90 seconds as well, because the software, which is auto-second, it can derotate the planet itself when you're stacking without an external software. So 45 to 90 seconds, I would say. And Saturn is 120 seconds. You can also take maximum to 2 minutes as well. So this is the maximum duration of a single video you can capture. If you capture beyond that, then you will not have a sharp image. And Uranus and Neptune, it depends. Like from few minutes, also you can take like up to 10 minutes as well. And the number of videos also matters. So if you want to take like rotation of the planet, then you have to take many videos. If you want to capture more details, then what you can do is you can take multiple videos and you can stack, and you can derotate all the images with one picture, so you get most of the detail. So that is called derotation, which is a special software. So here, few of the softwares: image pre-processing, planetary image pre-processing, which is PIPP. This stabilizes the videos at the center. And AutoCircuit software doesn't. It has that option internally, so it has that algorithm. So you don't need to stabilize a video in this PIPP software separately. If you have an image file, if it is not very shaky, then you can load it directly to AutoCircuit, and it aligns the object at the center automatically. And then the Registacks to sharpen it, Photoshop to process it, WinJupos to derotate the image, and impact detection software. If you have planets like Jupiter and Saturn, always you upload the video file into image detection software, so it will detect for possible impacts. So let's say if an asteroid is impacting the Jupiter, you might not notice it when you're stacking, and it cancels the bad frame, cancels the frame as a bad frame in this auto circuit. But you can detect it in this software, and you can report it to the professional astronomers, which will be helpful for them to understand about the planets. So this is one thing that you can contribute. And archiving the entire data, so you have to compress the file, because these are like tons and tons of GBs, and you have to compress the entire file. Otherwise, you will need to buy a lot of hard disk to upload it there. Also, you can convert the video file to a more smaller file. Like for example, the AVA file can be converted to X video file, which will take much lower space. Like you can reduce it to a few MBs instead of GBs. And also you can export it to, or you can burn it in a DVD if you want to use that file later on. So always practice with the data you have captured, and practice in the upcoming nights. If you have also try reprocessing all your images, and join planetary imaging social media groups and astrophotography groups, and follow all the professional astronomers and professional astrophotographers and amateur astrophotographers. You will get a lot of tricks and techniques, and you will learn over the time, and you can master it. So that's it. That's the presentation. And I have few files. We haven't covered the processing. I guess I took a lot of time. So if in case we have time, I can cover that. Kirti?
We can take 10 minutes.
Okay. So I'm just going to show one example of how to stack the image. So I'll begin with this Jupiter image. So this is a software, AutoStackit, and that's how you will get. This is the video file, and you can just drag and drop it, and you will have two windows, to the left and to the right. The left window, you can see the details of the planet, and here are the settings. So just below the open tab, you can see there are two things. One is surface and planets. Surface is for moon and sun. So you have to enable only for that. And for the planets, make sure you check the planet tab, and then check the dynamic background, and keep gradient. If you're using planets like Jupiter, Venus, Mars, and Mercury, which has phase, then you have to keep the edge. So let's say if I have Venus here, I'll show it quickly. So this is Venus here, and for Venus, you have to check the boxes which has the face, so that you will end up with sharp edge. Otherwise, you will have fuzzy edge. So this is for the planets which has faces, and Mars also exhibit faces sometimes. So now let's go ahead and process this. For Jupiter, I don't need to keep this. And once you check this gradient, and below, make sure it's in local alignment points. So these takes a longer time to explain all the features of this. Let's keep it this way. These are the ideal things that you have to keep. And then analyze. When you hit the analyze, you will notice here on the right hand side, you will see buffering and image analysis. So what it does is it analyzes the entire video frame, and it sorts the best out of it, and it gives you a graph of bad quality frames and good quality frames. And also it will give you a reference image to stack on the top of it. So I have 5,000 frames overall, and if you have a fast machine, then it takes only less time. So mine is I have 16 GB RAM, and it's kind of not very fast, so it's okay. So you get the processing done very quickly. And here you can see the graph. So this is a quality graph, and the background gray line is the allocation of the frames, and the green line, that's the quality of the sorted frames. So the top left shows you the higher quality frame, and the bottom right shows you the lower quality frames. So that 50% line, so whatever the things below 50% is bad, you can say what it is below 70% is very bad, and the top is good. So this is confusing for a few people, even for people like me. It's a bit confusing because you always look for the green graph, ignore the gray line. So always keep for the green line and make sure the top left is high up. If you see the graph on the top, then it has good quality frames. When that green graph goes down, then it's bad. So here I have a mix of that, so I can stack 70% of the data. So what I'm going to do is, before stacking, I'm going to just place alignment points. So you're going to keep some points, and it will use those points for the stacking reference. You can make the points automatically, or you can also use place AP grid. So this will keep the points automatically. So just by clicking it, it will just fill over. And also you can increase the brightness, like from 0 to 10. So it will only place the points on the planet. If you keep it at 0, then it won't. If the planet is dimmer, like Saturn and all, it will be dimmer. So you can increase the brightness on the top right under the display option. And this will digitally display, increase the brightness only for the stacking, but end result will not be like this. This is only for the stacking purpose. And ideally, you can use 48 alignment points, and you can just place the AP. And here you can see, since it's too bright at the center, it's not keeping the alignment points. So by reducing it to normal brightness, it will, yeah. So here you can either enter the number of frames percentage or the number of frames manually, or you can click, you can just press Alt and click, sorry, Control and click at the graph, and it will choose the frames percentage automatically here. For example, I'm keeping it at the center, which is 50%. And then make sure the normalize stack 70% is checked, and sharpen, this is checked, and RGB align is checked, and save in folders is checked, and simple file name for raw is also checked. And then stack. The drizzle data, that's for higher resolution. So if you have lower resolution image, if you want to make it as high resolution, then you can keep this 1.5x. So it will increase the resolution to 1.5 times from the previous one. So in this case, we're not going to use that. Just stack, wait for a while. It will align the images, it will stack the images. And if you have Registacks installed, make sure the software is open. So after stacking it, it will automatically load it to that software. And then you can just sharpen it, and then you can get the file. It's going to take a few seconds. Generally, image stacking takes longer than other options. Yeah, it's done. And here you can see it's automatically opened in Registacks. So at the left-hand side, you can see wavelets. So this is a powerful tool to sharpen it. So here you can see there are different layers. So ideally, you can choose the first 2 layers. Just move the slider, and you will notice the sharpness will be increased, and you'll get a lot of details. And also you can play with other sliders to get the best out of it. So now you can see a lot of details. And after this, once you sharpen it, then you can go to the right hand side, and here you can correct the color. You can just auto balance, and you will see it corrects the color automatically. Also, you can do it in the post processing in Photoshop. Then save the file, and then you're done. So that's how processing is done. And the more advanced thing is de-rotating the image. That will be too technical. Maybe we can cover it later. So all these planets, data of the planets are uploaded in the drive and which has been shared as well. And also there are two softwares which I've shared. So you can download it and you can practice at your home. And if you have telescope, you can just try the things which you have learned in this session. I hope you enjoyed. Sorry for taking too much time. We'll finish it.
Hi, Prabhu. You were exactly on time. So the session was supposed to be till 8:30, and you have exactly finished and managed the time really, really well.
Okay.
Thanks for that.
Sure.
So, Vishwa, do you want to ask some questions that people have asked in the chat window?
Yeah, yeah, Kirti. So we have a few questions that have been lined up. So I'll start with the very first one. So Aditya has asked about 3 questions. So first one was, I wanted to ask if we can use good quality webcams to take photos and videos. So what kind of webcams?
So if you have existing webcams at your home, you can just try using it. You may not find adapters perfectly for your webcam, but you can do some DIYs, or you can just attach your webcam to the eyepiece using a sellotape. That's how I did it, and see if it works. If it works, then you can make some pipes, PVC pipes from the hardware store, and you can make yourself one if you want to do it yourself. Because these webcams are meant for other purposes, not for planetary imaging. So in that case, you need to do it yourself. If you don't have a webcam, I would suggest you to get webcams like Philips Taucam. So these are some nice webcams which I will share the links for those webcams. And if you can save some more money, and you can get a planetary camera for less price. The starting price for a planetary camera, I don't remember the exact price. I think it's some $100. There's one brand which is called ZW, and there is one camera called 120MC. That's the beginner level planetary camera, and you can get amazing results with that if you can save some money. But if you are limited to the budget, you can try the other option. Yeah.
Second question was same from Aditya. So the extender, what does the 3x in extender mean?
So it's basically multiplying the focal length by the times of this. This is 3x and this is 2x, and the other one is 5x. This is 5x. So let's say my focal ratio is 4.5, and if I add this, it will be magnified by 2 times the 4.5, and this it will magnify it more. So the focal length increases. For planets, you need to have longer focal length because you need to magnify to that much to cover the detail. So always use 2 times or 3 times magnification for the planets if you have telescopes like f4.5 or f5 or f6. Even for longer focal length telescope like f10, still people are using 2x Barlows and 3x Barlows to get a close-up image of the planets.
Okay, moving on. The processing softwares, I mean, the capturing softwares, do they work only with popular CCD cameras, or what kind of devices will it recognize?
So the processing capture softwares which I have shown, those only works with popular cameras, and you can see a bunch of brands mentioned there. And if you don't have that brand mentioned there, then it will not open up. So in that case, you have other softwares which I don't know exactly because it's been a long time. But there are a few softwares which you can use if you don't have that specific software. I'll just go through it and I'll find the link and I'll share it in the group.
Okay, moving on. So Kumar has a question. How do you know the amount of zoom while using CCD camera?
Using the CCD camera, you mean what's the maximum limit?
The zoom. From what I believe is, smaller the sensor size, we'll get more magnification for the same telescope. So how does the chip size basically question is about chip size.
Right.
Isn't it about the binocular?
No, not.
How to know the amount of zoom with 10x, 50x? Oh, okay. It's not binocular. I thought it was.
No, it's not binocular. Like for example, if I have a 500 focal length and lens or even a telescope, and if I use a webcam, I'll get more magnification. But if I use a DSLR, I'll have a smaller magnification. So how does the chip size?
Yeah. So that is always manageable only with the extender or the Barlow lens, irrespective of the sensor size. It matters, size of the sensor matters, but the amount of magnification can be only made with a Barlow or extender. So if you have a DSLR, if you have a webcam, and if you have a telescope, to increase the magnification of the object to fill the entire field of view, then you have to use a Barlow or extender. And in the presentation, I had shared the ideal thumb rule of the focal ratio and then sampling. So there you can use like 3.5 times if the seeing is good. You can increase the magnification 3.5 times if the seeing is good. So you can use 3x Barlow with your telescope if the seeing is good. If it is not good, you have to use it lesser than that, like 2x, perhaps 1.5x.
Okay. Ravi Kumar had a question. So what exactly is Barlow lens?
So it's nothing but it magnifies the object, just like the eyepiece. So you have eyepiece ocular lens, and you have different powers like 20 millimeter, 15 millimeter, 10 millimeter. So when you put the eyepiece into the focus of wheel, you will see the objects, it magnifies as the the power of the focal length decreases. In the same way, so magnifiers or the Barlows or focal extenders, it magnifies the object, and you can see it bigger. So just a magnifying glass, to keep it very simple. Yeah.
Moving on, Satya Narayana Sridhar had a question. How effective is visual light pollution filter in case of planetary imaging? Light pollution filter.
For the planets, light pollution is not a major thing. Since planets are pretty bright, so you don't need a dark sky to image planets, unless the light source affects the imaging source. Like if the light hits the primary or secondary mirror, in that case you're going to lose some light. So make sure you cover that. Unless and until it doesn't affect the primary or secondary mirror, then there is no need of going to a dark sky. Yeah, but it gives you better viewing. But it's not mandatory.
Does it improve the resolution? Does it improve the quality of the picture if we use light pollution filter?
Light pollution filter to some extent, yeah.
Okay. We have another question on cropping video in sharp cap. So the question, the more details of the question was, my video of Jupiter shows planet in one corner. How to crop it and zoom it?
In one corner, in AutoSocket or in which software?
Sharp cap.
Right. In Sharp Cap, you cannot center it. Only in File Capture you can center it. If you are capturing the video in Sharp Cap, if the object is in the center, then you can load that in AutoSocket. For example, I have the AutoSocket here. Let me just show it. So hope you can see it. Yeah. So here you can see it automatically centers the object. So no matter where the object is, whether it is in the corner or bottom down or top left, when you load it in the AutoSocket software, it aligns the object automatically at the center. And only for the moon, the surface, you can keep some craters, and you can use these alignment points to keep it at the center. And also you can move it left and right. It's only applicable for the moon, but for other planets, you can automatically center it when you load it to the AutoStack.
Okay. Moving moving on. Uh, Image video stabilization in AutoSCAD. How to do that?
Image stabilization, you don't need to do anything. Only you have to just click the button. So it's straightforward. Like I said, by clicking this analyze button, it will analyze all the frames and it stabilizes automatically. You can see at the bottom, at the right window, you can see the surface image stabilization. It's going on. So which means it's stabilizing the image. So it does it automatically.
Okay. Thank you. Moving on. Swaroop had a question on how important is secondary mirror alignment
It is
in
very crucial. It's very important. Otherwise, you will end up with very bad imaging. So that's why before imaging or observation, we need to make sure that primary and secondary is aligned each other.
uh, in addition, will an artificial star collimation help in achieving better primary mirror alignment?
Yeah, artificial star also helps attaining a better collimation. If you don't have stars, if you want to do the collimation inside, yes, it helps.
Yeah, and the question was about one of the image which you had shared, which had that airy disk. I believe the question was eventually to how to capture that airy disk.
Which one capture what?
Airy
I
disk.
think the first question was what is an airy disk? So people got confused
Okay.
that it is an out of focus image. So maybe you can explain what an airy disk is and how to capture that, or how
Yeah.
to see whether it's
Right. So area disk is nothing but the diffraction pattern of a star or any bright spherical object. So when you point it towards a star and you just defocus it back and forth, you will see star and circular patterns around. So there are two things which you can notice by looking at it. If the scene is very bad, you won't see a perfect circle, and if the telescope is not very well made, if there are some errors in the telescope mirror, then it won't be accurate. So these are the two things that you can find out by looking at the array disk.
Yeah. What is the minimum altitude for good seeing?
So irrespective of good seeing, always capture when the planet rises high above with respect to the location. So you always look for the software and calculate the highest position when it crosses the meridian, the highest point in the sky. So always calculate that time and do the imaging in that particular time. If let's say if, it depends from location to location. For 10-degree north, people like in Tamil Nadu and in Bangalore, for them it goes like 50-degree above the horizon. And for me, where I'm living in 25-degree north, for me it is below 40-degree. So I have to wait till it gets 40-degree and then I have to capture. So it always depends on the location, and also check with this software to find out the exact position of the object.
Okay. We have one more question from Rahul.
Mm.
What is the best place online to buy telescope accessories, T-adapted tearing?
What is the best place?
Yeah. The price is almost 2 to 3
Yeah,
I
in
think by
Amazon or
best place he means best online website or
uh,
something like that.
there are many websites. Even in India, there are many websites where you can buy tearing and tear adapter. There is one of our friend who is manufacturing all these adapters and astronomical things. Kuldeep or Orion Astronomical Observatory. So he makes a lot of things and he can custom make it as well. So he's also in Indian Amateur Astrophotography Group, and there are many other online websites. Like you can also get it from Amazon, Amazon.in. You can get it, but I think it's a bit expensive. Also, you can get it from abroad. You can import it, but since these are like small things, I think the shipping will be too much. So it's not worth getting it from abroad unless if any of your friends or relatives traveling from abroad, you can ask them to buy it and you can get it. So you can get it for cheap. Otherwise, you can get it from India. Like I said, you can buy it from Kuldeep, or you can buy it from Amazon. Also, you can buy it from eBay as well.
Okay.
Also, many of these are available on AliExpress, right? And
Yeah,
probably it
AliExpress.
would be cheaper.
Yeah, AliExpress is cheaper, but at this present situation, shipping is going to take forever.
Yeah, that's true.
Some online groups to get tips from other astrophotographers. Can we share a list?
The list of the online groups.
Yeah.
Yeah, we can share it in the group, no? Like astronomy, planetary imaging, and planetary imaging groups and lunar imaging groups. There are like 4 or 5 groups which are dedicated for planetary imaging. So we can share it in the group following with this session. We can share all the resource materials, like the links for the websites and links for these groups. We can share it all together so that everyone can get benefit out of.
Yes, please join our BAS WhatsApp group if you are not in that already. That group is, if you join that group, you will get links to other groups.
Yeah.
Okay, so probably we'll take one final question. So Aditya has a question on utility of laser collimators. So is it actually useful or not? How effective?
Yeah, laser collimator is useful. I find it very useful comparing to the Cheshire eyepiece. I use it a lot, and it makes your life easier. That's all I can say. So you don't need to fiddle around. Just keep it in the eyepiece, and you can just check the primary and secondary, and you're done. And you can repeat it throughout the night. Yeah.
Okay.
Okay. I think Shubhankar wanted to say something, but I didn't understand what he was saying. He said, no, really, what about 1:1 live view in DSLR? Shubhankar, do you have something to say?
It was about, we are talking about magnification sometime back. Can you guys hear me?
Yes.
Yeah, we can hear you.
Yeah. So you were talking about magnification, I think in that context, I forgot. So you talked about, in the everything remains same. What you see, the image projected on your camera sensor can be magnified if you go 1:1 live view. Certain DSLRs offer that, and isn't that a a recommended way of capturing?
Yeah, that's what I mentioned. In particularly in DSLR cameras like 600D, you have digital zoom, 1.5 crop factor. So there you will get 600 by 400 pixels, and it increases the magnification there.
No, I'm not talking about the crop factor. Crop factor is the crop factor with respect to 36 mm full frame versus APS-C. That's called the crop factor. But in the live view of the DSLR,
Yeah,
there
that's what
is
I'm
a
talking. No, the crop factor that I'm talking is not with 60, the full frame camera and the crop sensor camera.
So
This is a digital crop factor, which are in few cameras, not all cameras. For instance, in 700D there is no such crop factor, but the previous version has. So to get that, yeah.
So my point was, there is a way to get more magnification of what you're seeing in the live view of your camera if you switch the live view to 1:1.
Yeah.
So So that's all I said. Nothing else.
Right. Yeah, it's similar to what I've said. Using the digital crop factor, we can get more magnification. And
Okay.
I'll share the output with the same magnification, so people understand how it works. So this is with 700D and 1.5x crop factor. Yeah.
Okay. We have one question on the. Can I have a short recap about in focus in DSLR?
Yeah. So I'll stop the in focus issue is a common issue in most of the bulk produced reflector telescope which are for observation purpose. So you have the secondary mirror, and the focus for observation telescope, it is inside the focus away. It doesn't get out. For only astrophotography telescopes, it comes out, so it has enough back focus and in focus. But telescope like this, since the focus is inside, you cannot reach the focus with the DSLR camera, because DSLR sensor has sensor inside, and plus you're adding this much of portion on the top of the sensor to connect the camera with the telescope. When you add this, and this is the barrel which will be blocked by the focuser itself, so it doesn't go further in. Since it's not going further in, you will have the focus point somewhere here on the silver ring, and the sensor is somewhere here on my palm. So you have this much of distance, so let's say 5 centimeter. So since the in focus is short in 5 centimeter, you will not have enough focus. So to get a focus, you have to either add the Barlow lens, have to push the mirror up. So these are the two ways.
Okay. One final question for the day. So some comparison between smaller refractor versus bigger reflectors in terms for planetary. Smaller reflector versus bigger reflector.
A bigger reflector. Refractors, they are good for planetary, but to a certain extent. And also, bigger the refractor goes, the higher the cost goes. So if you want to be if you want to have it with less cost, you have to go for bigger reflectors. And of course, bigger reflectors are proven good for planetaries. All the telescope designs out there now, everything is reflector in one way or the other, like Schmidt-Cassegrain or Ritchie-Chrétien or any other Maksutov. So all these are reflector type, except few models has some lens on the top. So reflectors are good for planetary if you're going for less cost. And refractors has some advantage, but not all refractors. Achromatics are not great. It's good for observation, but you will suffer with chromatic aberration around the edges. And only apochromatic refractors are good for planetary photographies with higher focal length, but it's way expensive than a typical reflector telescope.
Okay. I guess we have concluded all the questions. On a closing remark, I would say, Prabhu, it was a very great presentation. Thank you very much. So we'll start taking feedback from all the participants over the WhatsApp group, and we have also shared the few of the sample images which Prabhu showed during the demo, as well as the softwares in the Google Drive. And the same will be shared over the WhatsApp link as well as the Google Groups link. And yeah, please share your feedback on the format, on the content and everything in the WhatsApp group. In future, we will plan to have a few more sessions on this. So we have a few more topics that has been planned, like introduction of to basic equipment, portable equipment, deep sky as well, which we'll be taking it in the coming days. Thank
Sure.
you. Thank you very much.
Thank you. And also one thing to mention, to check out my entire journey, like all my images starting from 2012 till now, you can check my website and you can learn a lot as well. So I always mention how the work is done, so you can get some tips as well. In my website, prabhuastrophotography.com, you can see all types of images, from planetary to deep sky. So even I have divided further into further classifications. You can see the website and you can get an idea.
Okay, thank you so much, Prabhu. That was awesome.